Okay, so
So let me ask you a question. So in order to figure out what's going on, my cells or tissues have to respond to magnetic fields. Is that correct?
electromagnetic fields, yes.
So then how come I'm not pulled this way when I get around a magnet, or I'm not pulled this way? Why is that if I'm magnetic inside?
Well, we are not really magnetic ourselves.
But I do respond to magnetic
the
fields?
nuclei are themselves magnetic, but they're very tiny.
So anyway, since I do respond to magnetic fields, is this a safe therapy? Is this a safe
Yes,
technique?
absolutely.
Completely safe.
It's non-invasive. It's very safe. Nothing has been shown to be harmful. It has to do with MRI. Maybe accidents do happen because these are strong magnetic fields. And
So do you know of any accidents that's happened?
but I know that things just could, if you inadvertently come in with something that's metallic, magnetic rather, into the room where there is an MRI going on, an MRI scan going on, this could actually become a projectile because the magnet will suck it in. And so there has been, as far as I know, there have been some accidents in which people actually get hit by oxygen tanks that happen to be made of the wrong material. And
So that's the only danger, is being, hit by flying at metal objects, right?
Yeah, because of the strong magnetic field.
Did you read about the policeman whose gun went off or something?
Yeah, I think that happened somewhere in New York. It was an interesting
Do you know about this?
accident.
Can you tell us about this?
No, I just what I read in the news, basically. I don't know the details, but yeah, basically he was allowed to go in the room with a gun. He was an off-duty police officer, as I understand, and he was carrying his gun, and he asked if he could go in with his gun, and he was told yes. I mean, it was like several mistakes that happened. I don't think it was anybody's like intentionally asking him to do that. But in the end, he did. When he was pulling his gun to put it on the table, he was in the room with the magnet, and the magnet pulled his gun off his hands, and the gun went into the magnet, and the spontaneously got set off.
And was anyone hurt?
No, there was no.
That was a lucky thing.
That was a lucky.
So I know of someone who went for an MRI scan, and it was discerned that he had some metal in his body, or a bullet that was never removed, and then he could not continue. They wouldn't let him go for the scan. Do you know why that would be?
I can only guess. If it's lead, lead is not magnetic, so it, in principle, should not be too much of a problem. But when you do an MRI, you actually do change the magnetic fields very rapidly. That's the field gradient that you hear the thumping of. What the way that works is that you have to change an electric current very quickly, very fast. And metals, when you change magnetic fields and currents in a metal, metals do heat up, they warm up by the currents, the eddy currents they're called, that happen.
So in other words, he could have gotten like maybe cooked from the inside or something?
So he could, the bullet could get hot in the magnet while they're doing the MRI. And that's my guess.
And he could have had his tissue burned?
So he could, feel uncomfortable, if nothing else, or sometimes feel like that something's burning him.
Let's talk about the research you do. You do a lot of your research at the university where you teach?
Yes, I do. About half of the research I do is done locally at the university in Los Angeles, California.
And I heard you're getting a new lab. Can you tell us about that?
Yes, we're getting a brand new science building. We already have basically two wings of new buildings, and Wing A has been in operation already for a couple of years, maybe longer by now. And Wing B is almost there, and that's gonna be where I'm gonna be going next year.
You got a lot of pretty good toys coming with you, right?
Yeah. Since this is a new building, then there are funds available to get
so what are you
infrastructure. Getting? Oh, we're getting. Excuse me. We're getting. One of the most interesting things we're getting is an atomic force microscope.
Tell us about that.
Yeah. Basically, with NMR and MRI, you can see inside things. at the microscopic level, and that's without, but these are bulk, big things. An atomic force microscope can be used to see things that are very, very small themselves. So, for instance,
So is this better than in an electron microscope?
Not necessarily. It just depends on what you're looking for.
Uh-huh.
But this atomic force microscope is designed to be able to see objects like, say, that are the size of an atom. So you can actually see the structure of the material at the scale of the atoms.
So you could see the structure of the metal you're studying?
Yes, for instance, that's correct. You can see the atoms being lined up in different patterns. And so you can study surfaces, and you can study all sorts of properties. There's a lot of chemistry that goes on in the surface of a material. So you can do a lot of studies on that. And this, the size of the object that you look is really atomic. In other words, so you can do nanomaterial studies. A nanomaterial is a material that is so tiny, it's of the order of a few atoms wide or big.
So what else are you getting?
We're getting a magnetometer, which we did not have for forever. So
I don't know what that is. What is a
that
magnetometer?
That is
Explain, because I don't know if any of us know what that is.
Okay, well, basically what that is it's a machine that allows you to understand how strong a magnet something can be. But these are tiny magnets, like, let's say, you can put a nanomaterial in the magnetometer and find out if it has magnetic properties.
So it tells you how strong a small magnet is?
Yes, yeah.
Why do you need that?
Well, magnetism is a very complicated topic, if you want to put it that way. Understanding magnetism is one of the biggest challenges we have in the field.
Is it still an enigma for physicists?
Yeah, we still don't know exactly. Well, we know where it's coming from. It's coming from the electrons themselves. The electrons are magnetic themselves, and how they organize themselves into the material will determine what kind of magnet they are. And so we know that, but we can hardly predict how a material is going to behave magnetically, beforehand. One way to do what we do is, after the fact, basically, we can measure, we can put this material into the magnetometer. And then
so you got your microscope, your magnetometer. What else are you going to get?
We're going to have an X-ray machine that can tell us about the crystallography of the materials.
Uh-huh.
And that means crystallography, meaning how the atoms are organized inside the material. And we're going to have some cryogenic equipment that will allow us to go to lower temperatures.
How low?
Well, we won't be able to go below 1.5 Kelvin. That's
superconductivity. Watch out, huh?
Negative. No, that's not very high. I mean, that's not very low. It's not very high.
1.5 Kelvin is not very low?
Well,
sounds pretty low to me. How low is the lowest temperature that is possible? 0 Kelvin, right?
Okay, in condensed matter, we can go to a few millikelvin. That's 1,000. A millikelvin is 1,000 of a Kelvin. So 1.5 Kelvin is like 1.5
that's hot, huh?
That's
too hot for you.
That's very hot.
But it doesn't really go below 0, does it? At all, ever,
no.
Huh? The scale just stops right there, right?
The absolute scale stops at 0, yes.
And it goes as high as you want, right?
Yes, that is true. Yeah, like the temperature of the sun inside the sun or the big star would be very high.
Well, we don't want it to go that high.
Millions of degrees or so.